Hello everybody. Today we are going to go over forces. By the end of today you're going to be able to explain and understand balanced and unbalanced forces. So as we see here today, our title that we were going to start off with, so if you want to turn to a brand new page in your notebook, title it Balanced and Unbalanced Forces and Combining Forces. Give you a moment to do that. Make sure you put today's date. We will have a CK12 at the end of class today, as well as a worksheet that goes along with the ideas and concepts that we are going to discuss today. Make sure to take notes, and if you have a highlighter, that'd be great to have out, as well as a pencil, and we can get started here shortly. All right, so some of you have gone rode a scooter, a skateboard, a bicycle, pushed a shopping cart, right? But we see Carson here, and Carson is riding a scooter, and as you can see, he's pretty good at it. The idea that he can do tricks in the air, lots of practice, but in order for Carson to move, there has to be some type of force. Right, so he's getting his scooter started by pushing off with his foot, as you can see here in the right-hand picture. And with that, the force that he applies to the ground with his foot starts the scooter moving in the opposite direction. So the harder he pushes against the ground, the faster his scooter will go. You've all experienced this in some way or the other. And so we look here, and this would be a great time to pause and let you guys write all of this down. Now that you had a chance to write this down, a force is a push or a pull exerted on an object. So you see these top pictures up here, the ones on the left, right? There's a push, right? As you can see up here in the, let me see if I can get my pointer going. There we go. We can see right here that with this stance right here, you can see that the push would be a lot greater. And so what we would see here is a normal push would be F, right? And a harder push would be 2F, right? 2 times the amount of force is being applied to the cart. And you can see that because he's kind of in this running stance. So again, a force is a push, right? So you push up against the wall, or you pull. If you're like me, if you never look at the sign on the door, push or pull, I feel like for some reason I always do the opposite of whatever it is. If it says push, I'm usually trying to pull it open. If it says pull, I'm trying to push it through, right? I don't get it. It might happen to you as well. So a force is described by its magnitude and by the direction in which it acts. Okay, so again, magnitude is the strength. So if you're like, what is magnitude? Magnitude is the strength, right? And by the direction in which it acts. So we would say that this cart is being pushed in this direction, right? If the arrow was going in the opposite direction, we would say the cart would be being pulled, right, to the left, but it is being pushed towards the right. So we have direction, and then we have the strength. And we would see here that 2F would be the strength, how much force is there. 2F would be greater than F, right? Now we talked about our SI units, and so our SI unit for magnitude of a force is what we call a Newton. We are going to be going over Newton's 3 laws of motion here very soon, but the idea that a Newton is abbreviated with a capital N, right? And a Newton is 1 kilogram times meters divided by seconds squared. And I'm going to show you that in a moment here, but I'll give you a moment to write that down. If we need to pause, go ahead and push pause now so everyone has a chance to get that written down, and then move along as we see fit. All right, so that's what I was telling you about right here. And I put this slide, same slide as before, but sometimes we just don't, this linear format, we don't always see it. But what this right here means, it means divide, right? So it's kilograms times meters divided by seconds to the second power. So it's like seconds times seconds, right? Second, if we have x squared, it's x times x. So we have 5 squared, we have 5 times 5. Same with a unit, right? So it's seconds times seconds, or seconds squared. Right? So that's what these are. These are the units that we would use. But we abbreviate it as a Newton, right? And you can see why we'd want to abbreviate that as a Newton, right? Unless you want to write kilograms times meters divided by seconds squared every single time. All right. Force as a vector. Now we might know about vectors from math class. Now I taught 7th grade math, so I'm pretty sure that we have drawn arrows before, right? And arrows are pointing in one direction and they go on forever. Now a vector, as you might know, ends, right? It has a set and stop point. So if we're looking down here at our diagram of force A and force B, we can see that the different lengths, right, would represent the magnitude and then the direction in which it is pointing, right? Because if we go back, we know that force is described as magnitude, its strength, 1, and 2, its direction. Okay, so force is a vector or a measure that has both size and direction. Vectors can be represented with an arrow. The length of each arrow represents the strength or magnitude of the force, and the way the arrow points represents the direction of the force. So if we're looking at example 1 here, the two forces applied are in the same direction, and force B is stronger than force A. Now force B is strong. How do we know that force B is stronger than force A? Simply by the length of the arrow. The length of the arrow is the magnitude. It's the strength. Okay? So the longer the arrow, the greater the force. The shorter the arrow, the less force that is exhibiting. So we would see that force B is about 2 times the force of force A in example 1. Now in example 2, we see that the forces, they're equal, right? They're about the same exact length. Now, if we had to get out a ruler and measure it, I'm not sure. But, looking at it, eyeballing it, we can see that force A is about equal to force B. But there's something going on here. The two forces are applied in opposite directions, right? And when we get to adding these forces up and looking at combining forces, we would see that it would actually be a 0 force, right? And because force A would cancel with force B because they're the same size and they are in opposite directions, right? So we'll get there soon. Two forces applied in opposite directions with force B equal to force A. So drawing these diagrams in your notebook would be great. If we need to push pause, again, go ahead and push pause. Get this written down into your notebooks, and we can move on. Now what we're seeing here is different examples of your daily lives in something that maybe you've done before, right? We can all take up our hand, take one hand, take our finger, and we can apply a force, right? So pick up your hand right now, hold it flat at like the top photo up here, right? And then go ahead and push against it, right? You were applying a force towards your hand. Maybe you've walked across the street before, right? You've pushed the button, right? You probably didn't know, but you were applying a force to that button. Maybe you had to push something real heavy, right? Your mother or your dad or your brother or your sister wouldn't get out of the way, right? And you're just pushing them across the floor. Or maybe you have a box that you need to get out of the way, right? And you can't lift it because it's so heavy, but you push it, right? Have you ever done a push-up before? Everyone's favorite, right? Or you haven't done this in your life yet, but soon enough, you might have to be pushing some type of vehicle. Now these people look like they have their work cut out for them being that this van looks completely packed, as well as inside, as well as on top. I'm not even sure how they fit in there, but they must. Right, here's some examples of a pull, right? We do pull-ups, right? We pull our bodies upward, right? Maybe you have had one of these fun rolly backpacks, right? You're pulling it behind you. And here's all my favorite, right? Every time I see this, I'm not sure why, but my brain thinks opposite, and I usually push instead of pull, right? Little brother's down here saying, "Come here," pulling them backwards, right? As well as you can see that this person up here is trying to pull their horse, but the horse is pulling backwards. So we have push and we have a pull. That's what a force is. Now we're not going to go into breakout rooms, but here's some time for you to go ahead and answer these 4 questions. So I'll go ahead and ask the teacher in the room to push pause, give you a moment to answer these 4 questions. All right. So number 1, is the man pushing or pulling, right? And if you answered pulling, you are correct, right? He's pulling the crate towards him. What is the term we use to describe the red arrow, right? What is the term we use to describe the red arrow, right? And that would be force, right? This represents the force being applied. How does the length of the blank describe the force? How does the length of, how does the length of the force describe, the arrow describe the force, right? So the longer the length, the greater the magnitude or the strength, right? So again, the longer the arrow is, the greater the magnitude. I guess I could have done that. And then lastly, what is the SI unit for the strength of a force? And that is a Newton. Right? So again, the SI unit, and that's kilograms times meters divided by seconds squared. All right. I'm going to ask the teacher to go ahead and push pause again. Let you get this written down into your notebook. These are some common abbreviations for us to remember: friction, normal force, applied force, and gravity. Right. So go ahead and get these written down. If your teacher hasn't already pushed pause, please push pause now. Let everyone write it down. Now friction, F of F, right, subscript F, resistance from surface contact, opposite of motion, right? Now if you've ever rubbed your hands together, if you put your hands together and start rubbing them together, you're going to start feeling some heat. Well, what's happening there? Your surface of your skin is causing friction when you move that together. There's a force that you're applying to your hands to rubbing them together, and the contact, the surface contact, and going in opposite motion directions is causing heat. Normal force, which is F of N, that's the force from an surface of an object. And applied force, this is something that's exerted, the push or the pull, right, on the object by a person or thing. And then F of G, that is just how much mass something has, right? If you're trying to move a heavy box on the ground versus a Kleenex box, right, something's going to have a greater mass pushing downward on it, right? The heavier the mass, the harder it is to move. Like if I sat on the ground and you tried to push me across the ground, it'd be a lot more difficult than if you tried to push, pick the smallest person in the room, right? And they tried to be moved across the ground. Right? So my mass is going to have a greater force pushing downward onto the ground than, say, your mass. All right, now we've all played this game before, and you know, boys, girls, who's gonna win? I don't know, right? Maybe we'll have to do this when I get back. Boys against girls it's boys against girls in this friendly tug of war. The two teams are pulling the rope in opposite directions. Which team do you think will win? Let me hear it. Let me hear it. It depends on which side pulls on the rope with the greatest force. As this example shows, more than one force may act on an object at the same time, right? So we have 1, 2, 3. Each one of these boys is pulling to the left, and each one of these ladies is pulling to the right, right? And so there's more than one force being applied, right? And so what we would do there is we would add up each one of these forces that yellow shirt, blue shirt, green shirt is applying to that rope. And if that force was greater than, say, checkers and flowers, blue checkers, green checkers, flowers, right, force, then you would see that this rope would go towards the left. Now, if the ladies had a greater force when they added up each one of those forces, well, then the rope would go to the right because this force would be greater than that force. As an example shows, more than one force. All right, read that. What would it surprise you to learn that at least two different forces are acting on you as you read this article? Can you guess what they are? Teacher in the room, please push pause. Let students guess what two forces might be being applied to them at this exact moment. All right. Now we're in a 8th grade science class, and which is heavily, not heavily, a lot of it's going to be some physics, right? And so we're going to spend the majority of our first trimester going over Newton's first laws and physics. And right now we're looking at a force of gravity, right? So this book is on this table because gravity is pushing this book downward onto this table. But the table pushes back with an equal force. And you're like, what? You're looking at your table right now, you're like, well, that's not pushing on anything. It is, right? So the table is actually pushing against, right? Otherwise, what would happen to the table? It would be smushed into the ground, right? So if the table wasn't pushing back against gravity, right? Well, the table would just fall to the ground, right? If you have a book in your hand right now and you pick it up and you hold it over the table and you drop it, well, what's going to happen? It's going to fall to the ground, right? Once it hits the ground is going to push back up against that book with equal force, right? If it didn't, where would that book go? That book would just go straight through the ground, right? And it would keep going and going and going and going, right? Nothing would be stopping it. So we have to think about that as a thing, as like, why don't we mush into the ground? Well, our bodies are pushing up against gravity, right? Gravity is pushing us down, right? Our bodies are pushing back up against gravity with an equal force. So one force acting on you and all other objects on Earth is gravity. If we look at this physics book and the figure, gravity pulls the book downward with a force of 20 newtons. So why doesn't the book fall to the ground? Well, the table is pushing upwards on the book with the same amount of force. The combined force, or net force, acting on the book is 0 newtons, right? That's what I told you when you combine them, right? Opposite forces, 20 newtons up, 20 newtons down, 20 minus 20, 0. That's because upward and downward forces are balanced, so they cancel each other out. In general, whenever forces act on an object in opposite directions, like the book on the table, the net force is equal to the difference between the two forces, right? So net force is equal to the difference, subtraction, right? In other words, one force is subtracted from the other to calculate the net force. If the opposing forces are equal or balanced, the net force is 0, as is for the book. That's why the book doesn't fall to the ground, but instead remains resting on the table. All right. So we're looking here now, a combination of forces, right? I told you we can always add these things up. Now we have these two little scruffers here, and they are fighting over this rope. Yeah, similar to the tug of war with the boys and the girls. The combination of all forces acting on an object is the net force. Right? Combination, right? Everything together. So a net force will cause objects' motion to change. Now, if little scruffers over here is pulling with a force of 10 newtons, and big scruffers over here is pulling with a net force of 12 newtons, well, big scruffer, he's gonna win. I know. This one's so cute. But this guy, he just has a little bit more force to give. And so what's going to happen is this rope is going to go to the right. And remember, a force is described by its magnitude, its strength, and by the direction in which it acts. So we have to answer this with two different things. We have to answer with the strength, how many newtons, and the direction that it's going in. So since big scruffers pulls with 12 newtons, little scruffers pulls with 10 newtons, we say 12 minus 10, that is 2 newtons to the right. Now if you don't want to write to the right, you can just draw 2 newtons and then draw an arrow. Okay? So again, when the forces are unbalanced, we take the larger force, we subtract the lesser force, we get the net force, and we give it a direction. Okay, so again, magnitude, its strength, how many newtons it is, plus the direction it's going in. So everyone hold up on your hands, show your teacher right now how many things you have to write down for an answer here. If you're holding up 2, you are correct. Right? We have to do magnitude in newtons, the strength in newtons, and direction. All right, so here we go. What is the net force acting on the object? Okay, so if we're looking at the soccer players right here, this gentleman in the red is going to kick this ball with a force of 125 newtons. The yellow guy is going to kick this ball with force of 75 newtons. So we would say 125 minus 75, and that would be 50 newtons difference. 50 newtons difference. And since red guy, shirt guy, is kicking the ball to the left, that's the direction the ball is going to go into. So we say 125 minus 75, which is 50 newtons to the left. The boys in the figure are about to kick the ball opposite directions. What will be the net force on the ball, and in which direction will the ball move? Again, you have to do 2 things here. All right. Combining forces. When forces act in the same direction, we add them. Okay? So in the same direction, we add them. Unlike here, we see that these people are pushing against each other. Green shirt pushes at 200 newtons. Pink shirt pushes at 100 newtons. The net force is going to be 100 newtons to the right. These are unbalanced forces. And this gentleman and this gentleman are moving this little pretty couch. I just wish I had one just like it, right? Anyhow, he's pushing, right, at 25 newtons, and this guy's pulling at 20 newtons. And so since they're going in the same direction, we add them, right? So when the forces are acting in the same directions, we add. When they're acting in the opposite directions, we subtract. Right? And so this would be 25 plus 20, 45 newtons to the right. Don't forget direction. All right. Now combining forces, if forces are equal in strength and opposite direction, there is no net force. Net force is 0. So elefante número 1, elefante número 2, they're both pulling with 200 newtons in opposite directions. There is no net force. Net force is 0. Green shirt, pink shirt, both pushing with 200 newtons, 0 net force. Again, the teacher in the room can push pause and let you copy anything down that you like. Drawing pictures, drawing diagrams, using different colors is always helpful in your notes. These are also posted on Google Classroom, so you can come back to them at any time you'd like and write down, print out, or finish up the notes at your leisure. All right, just a couple more examples here. As we can see here, we would have 10 newtons to the left. We would have 10 newtons to the, 10 newtons to the right. 10 minus 10, we would have a net force of 0, right? We would say this is a balanced, right? We'd say this is a balanced forces, right? We have 10 newtons to the right, another 10 newtons to the right. If they are in the same direction, we add. So we would say 10 plus 10 would be 20 newtons. Our net force would be 20 newtons. Now this is opposite direction, so we're going to subtract 10 newtons to the left, 8 newtons to the right. 10 minus 8, that would be 2 newtons, right? And remember, we have to have magnitude and direction, so we either have to draw an arrow pointing in the direction that we're going, or we have to say to the left, right? So 2 newtons to the left, or an arrow to the left. Editing here. One thing I want you guys to do right now is to look at each one of these A, B, C, and D, and I want you to calculate the net force, right? So it's going to give you some time to do that. Teacher, go ahead and push pause now. Oops. And go ahead and calculate A, B, C, and D and their net forces. All right, welcome back. We have 2N to the left, 2 newtons, and we have 8 newtons to the right. Therefore, we'd have 8 minus 2. It's greater magnitude on the right side, so we'd say 6 newtons to the right. Now, going in the same direction, we'll add them, right? So on B, we're going to combine them, right? 10 newtons and 2 newtons because they're going in the same direction. Therefore, we say 10 plus 2, and we say 12 newtons to the right. Now, we would say this is an unbalanced force, right? And this is also, A is also an unbalanced force. So A and B are unbalanced forces. C we would call a balanced force, in that there's 8 newtons to the left and 8 newtons to the right. Therefore, the net force would be 0, and we would say that that's a balanced force. And then lastly, D, we can see that there are 10 newtons to the left, 5 newtons and 3 newtons, so a total of 8 newtons to the right. 10 minus 8, an unbalanced situation here. We'd end up having 2 newtons to the left.